Hi everyone, Dr. Burns here with our next lesson in our chapter on acid-base equilibria and solubility equilibria. We're first going to discuss acid-base titrations, as those are how we experimentally determine our information about acid-base equilibria. In General Chemistry 1, we discussed briefly acid-base reactions, and we also discussed the technique used in the lab called titration. If you've taken the General Chemistry 1 or General Chemistry 2 lab, you are familiar with the technique of titrations. So here we're going to go into more detail about titrations with our new knowledge of acid-base equilibria. Specifically, we will be focusing on strong acid, strong base titrations, weak acid, strong base titrations, and strong acid, weak base titrations. So just some terms to remind us of titrations. We have two solutions. One solution is called the titrant. The titrant has known volume and known concentration. And our titrant is going to be put into our burette, which is the type of glassware that we use when doing a titration. It allows us to know the exact volume of the titrant that was added to our unknown solution. That unknown solution is called the analyte. The analyte has a known volume because we measured the volume before we put it into the container. However, it has unknown concentration, and as this is an acid-base type of technique, it also has an unknown pH. So the act of doing a titration is what is going to determine the concentration of the analyte. So the analyte is found in the flask. When we've talked about acid-base titrations in the past, and when we do acid-base titrations in our labs, we always do the math to find the concentration of our analyte by taking first the volume of our titrant and using that to convert to moles of titrant. Because if we know its concentration and we know its volume, then we're able to find the moles. If we know the moles of the titrant, and we know the reaction that's happening, meaning we have a balanced chemical reaction, we can use a mole-to-mole ratio to find the moles of analyte. And since we know the volume of the analyte, if we know the moles of analyte and the volume of analyte, that allows us to find the concentration of the analyte. Now, these are the calculations that we've done on titrations previously in General Chemistry 1 when we were learning about acid-base reactions more generally, and also talking about how stoichiometry can be used to find all of these values. Again, because if I want to go from moles of titrant to moles of analyte, we need to use a mole-to-mole ratio. If you recall from your lab, when we've done acid-base titrations, we always added an additional solution to our flask, and this was called an indicator. So when we add our base to acid or our acid to our base in a titration, the pH is going to change because we're undergoing a neutralization reaction. Therefore, we use a color indicator solution to tell us when the reaction is complete. These indicator solutions will change color as the pH changes, either from acidic to basic, like our solution would, or from basic to acidic, like our solution would, depending on what we're titrating. So different indicators have different changes in color depending on the pH where we would expect that acid-base reaction to occur at, or the pH where that acid-base reaction were to occur at. Now, how do we know this? Well, scientists before us have done all of the work for us, and they tell us, okay, if you want to do this type of acid-base reaction, use this color indicator because it'll change colors in the exact pH range that you want to know, and everything like that. But what they did essentially was they've tracked the pH changes of a titration versus the amount of volume of the titrant that was added, and they create something called a titration curve, which is what we have this on the screen here. We have our pH versus our volume of titrant. And in this case, we're titrating NaOH with HCl, okay, as well as acetic acid. So acetic acid is in purple and HCl is in red. So what happens is we can track both lines. If we start off with 0 volume of our titrant, okay, we start at our initial pH. That's just the pH of the acid solution, the weak acid or strong acid, whichever we're using, before we've added any base, okay? Then, as we add more base, that pH is going to slowly start to change. So we add more base, our volume starts to increase, and we start to see that our pH is starting to rise. Weak acids and strong acids are going to react to those pH changes differently, okay, which is why we prefer to use a strong acid over a weak acid in some cases, because they can resist immediate pH changes when we add base to them, okay. But what we see is that at some point, about halfway through this reaction, we see this vertical line coming in, okay, a big jump in our graph. This is called the equivalence point. That is when the reaction is essentially complete. We've used up all of our acid to neutralize the base that was being put in. So we can track that, and when that happens, and then that can indicate what color indicator we should use. So we can use phenolphthalein if we want it to occur between 10 and 9 and 8.5 for our pH. We can use a litmus paper. We have methyl orange. There's also methyl blue, methyl green. There's a bunch of different pH indicators that can be used depending on where the change in the pH is expected to be for that chemical reaction, for that acid-base reaction. So let's go more into these titration curves. Titration curves tell us the pH at all points of the reaction, and certain points tell us even more information. So here we have the reaction between a strong acid and a strong base. So let's say sodium hydroxide and HCl, like we saw in the previous slide. We can see again, this is exactly what we saw before, where we start to see a slight increase in our pH, and then at the volume halfway through, we see this big jump in our pH. We go from something that's acidic to something that is basic in essentially 1 milliliter of solution. So it doesn't take much for that pH to change drastically from acidic to basic. So again, this point in the middle is called the equivalence point. And this is when the moles of added base are exactly what is needed to consume the moles of acid in the original solution. Essentially, both of our reactants, all of our reactants, reacted together and there's nothing left, and we've made all of our product. We've neutralized our acid and our base, and we made our product. We have no reactant left. The change in the pH up here then just comes from the addition of more base, okay, leading to a basic pH. There's just more base than anything else, leading to why it's read as something past a pH of 7. Now the type of acid and the type of base is going to change what these titration curves look like. So here we have one that is of a strong acid and a strong base. We can also have a weak acid and a strong base, and a strong acid and a weak base, and their titration curves will all look different from each other. So let's look at what those titration curves look like and see the range in where we would expect the equivalence point to be for all of those reactions. So let's start off with our strong acid, strong base titrations, which is what we've been looking at so far. So the reaction between the strong acid HCl and the strong base NaOH can be represented by the following balanced chemical equation. NaOH plus HCl creates NaCl and H2O. Remember from General Chemistry 1, when we have an acid reacting with a base, we create salt and a water. So here we have a salt, and here we have water. If we were to look at this as a double replacement reaction, which acid-base reactions are, they are a special type of double replacement, we can define our net ionic equation, aka the ions that are participating in the chemical reaction. Okay, so the two ions that are participating in that chemical reaction are OH minus and H plus, creating water. Since this is both a strong acid and a strong base, we know that there is no equilibrium that is happening between them. They are strong acid, strong base, so they fully dissociate in water or in solution. So they're able to make this net ionic equation with a one-way arrow. Because we are creating water with our strong acid, strong base titration, the equivalence point, the point at which the reaction has completed and all of the acid and base have been used up for that net ionic equation for making water, the equivalence point will always be at a pH of 7. So for a strong acid, strong base titration, the equivalence point will always be at a pH of 7. And this is because in that reaction, the product that matters is going to be the water. Water, we know, has a pH of 7. So if we're mixing a strong acid and a strong base together, we're essentially making water. Okay, when all of that acid and all that base is used up, we're making water, and it's going to have a pH of 7. So if we see an equivalence point, so the halfway point of this kind of vertical line there, okay, if it's at 7, then we know that the reaction was between a strong acid and a strong base. Now let's look at if we have a weak acid and a strong base. So let's consider the reaction between acetic acid and sodium hydroxide. Now here I don't have sodium hydroxide shown because it is just a spectator ion. It's not participating in any part of this chemical reaction because we really only care about the acid and the base being the OH minus. So this is really Na plus and OH minus. But that sodium is really just a counter ion, and it would just go with that acetate ion in the product side. So once we have the reaction between the acetic acid and the OH minus, this acetate ion right here, the CH3COO minus, is going to undergo hydrolysis with water, meaning that it's going to form a type of equilibrium with the water that it first created as well as the water that was used to make these aqueous solutions. It's going to react with that water. So remember that when we have an acid reacting with an OH minus, this is going to be the conjugate base. The conjugate base can then act like a base and accept a hydrogen. So here it is down here in the hydrolysis where it's going to act like a base. And what's it going to do? Well, a base is a proton acceptor. So it's going to take the hydrogen from the water and put it right on here. And we're going to create that acetic acid compound again, leaving us with an OH minus left over. So this is again at an equilibrium because it's a weak acid and a strong base. Now this OH that's left over indicates something that is basic. And that's going to help us determine where the equivalence point is going to be for this weak acid strong base titration. So if we look at the titration curve for a weak acid strong base titration, our equivalence point is always going to be basic. So for weak acid strong base titrations, the pH will always be higher than 7. So it's always going to be in the basic range. You can also think of it as, well, if I have a weak acid and a strong base, if those two are competing with each other, the strong base is going to win out for when the reaction is going to be completed. So there's going to be leftover OH minuses in solution that go unreacted, resulting in a more basic solution when the reaction is complete. So we see the equivalence point being in the more basic range. Here we have it at 8.5. This is not a specific value. Okay, we'll just say not a specific value. It is a range Okay, it can be a little bit more basic, a little less basic. The only one that has a specific value is going to be the strong acid, strong base because of the creation of water. So that's the only one that will be at exactly 7 as pH. Everything else, so in this case the weak acid, strong base titration, is going to be anything higher than 7, and that's going to be a range of numbers depending on the weak acid and strong base that are being used. The only way to find that out is to perform that titration and track the pH with a titration curve. The last type of titration is a strong acid, weak base titration. The justification and understanding of this type of titration is very similar to the weak acid, strong base titration we just talked about, just opposite now. So consider the neutralization between hydrochloric acid and ammonia. Again, we're not showing the Cl here because it's a strong acid, so the only thing that's participating in that reaction is the H+. The Cl is not doing anything. Okay, it is only a spectator ion in that case. So we have H+ reacting with NH3, creating an equilibrium with NH4+, ammonium. So that ammonium is going to act like a weak acid. So remember, this is now the conjugate acid because the NH3 was the base. So the conjugate acid is now going to act like an acid. And it is going to donate a hydrogen because acids are proton donors. So it's going to take this hydrogen and add it to the water, creating again the ammonia that we started with and an H3O+. And we know from our discussions in our previous chapter that if we see an H3O+, we can assume that the solution is now more acidic. And we see that in our acid-base titration curve here. So we see that we start with now a more basic solution because we start with a base and we're adding a strong acid to that. So the pH is going to decrease now. So we have a small typo here. If it's in your handout, make sure you change this. This is for a strong acid, weak base. There we go. So for a strong acid, weak base titration, the pH at the equivalence point is going to be lower than 7. So this is going to be in the acidic range. And this is due to the additional H3O+ that are present in the solution when this reaction is happening. So we see again that this is not a specific point. It is again just a range where it could be. It's not always going to be at 5.5 pH. Okay, it depends on what the strong acid and the weak base are in that titration. But again, you can think of this since the acid is stronger, it's going to bring that pH down for its equivalence point because it's essentially going to win out over the weak base. Now, when it comes to determining exactly what these values are, we can do that not only in the lab using a pH meter, as some of you may see if you take the General Chemistry 2 lab, but we can also do this through calculations because we know that these reactions are happening in balanced ways. So we can use the information known about the titrant and the analyte and their balanced chemical equations in order to solve for concentrations at equilibrium, and so on. So, from a technique as simple as a titration is, if you've done one in the lab, you know they're pretty straightforward. We can obtain a lot of information regarding that chemical reaction, that acid-base reaction. So we will encounter 3 types of calculations when we're working with titrations, and your book goes through these 3 types of calculations. The first type is solving for the concentration of the analyte, which we kind of walked through a little bit before. We can then solve for the equilibrium concentrations for a weak acid, strong base, or a strong acid, weak base titration. okay? Because we know that if they're weak, either an acid or a base, it's automatically going to be in equilibrium. And then we can solve for the pH at various volumes throughout the titration. Now, this last one here, we are not going to cover, and it is not in your homework. Or in your exams. Okay, your book does go through these, so if you did want to go through those types of problems, feel free to read through that in your textbook. They just take a lot of time that I just don't see as completely necessary to be doing on an exam when you have a bunch of other problems that you need to be doing. I just think they take up far too much time, and each different volume that you would look at requires a whole additional ICE table and use of multiple different equations, and I just don't think it's a good use of your time, at least for when we're doing this on homework and exams. So we're going to focus on the first two for what you're doing in your homework and your exams, but if you did want to go through the various volumes technique for your titrations, feel free to read through that in your textbook. So let's look at these two types of examples. The first one is going to be solving for concentration. Now this is one that I believe most students are more familiar with because it is what we covered in General Chemistry 1, where you have to start with your volume of your titrant. We use that to convert to moles of titrant. We then use that to find moles of analyte, and then we can then find our concentration of our analyte. So that's going to be our steps for these types of reactions. So in a titration experiment, 27.5 milliliters of 0.50 molar H2SO4 neutralizes 5.0 milliliters of NaOH. What is the concentration of the NaOH solution? So if we look at what we're doing for this problem, where we take volume, convert it to moles, then go mole to mole, and then to concentration, we know that if we're taking a mole to mole here, if we want to do a mole to mole ratio, we must have a balanced equation. We need that balanced chemical reaction in order to do this properly. We can't go from moles of one substance to another without a mole to mole ratio, and we can't get a mole to mole ratio without a balanced chemical reaction. So let's look at what we are reacting together, predict our products, and balance our chemical equations. Now, we've done this before, and this is a concept that was covered in General Chemistry 1. So if you are unfamiliar or do not remember from General Chemistry 1 the predicted outcome of an acid-base reaction and how to go through these, please review that independently, because you will have to remember how to do that for these problems. So here we have H2SO4 reacting with NaOH, and we're going to create out of that, well, we know it's a double replacement reaction, so we really have H plus, SO4 2 minus, Na plus, OH minus. So we're going to have the H plus and the OH minus. That should be a minus, not a plus. There we go. We know we're going to combine those together, and then we're going to combine the Na and the SO4. So we get H and OH minus, that's H2O, that's water. And we are going to get Na2SO4. Remember, if I have a 2 minus on my SO4 and a 1 plus on my Na, I need 2 sodiums to balance out that charge. Again, that's just our basic rules of ionic compounds. Now we have to balance it. So we balance with a 2 and a 2. Again, I like to personally think of the H2O when balancing as an HOH. That way I can count my OH as one entity when I balance, keeping my polyatomic ions together. as our rule states in balancing chemical equations. So I personally like to think of water as HOH. That way I can see how many OHs I really need. So we can see that the 2 applies to that OH as it does down here. So that's our balanced chemical equation, and we definitely need that to solve this problem. So now we just follow our little guide here for what we have to do. So we take our volume of our titrant and we have to convert it to moles of titrant. How do we do that? Well, we have to use our molarity. Let's see. We know that H2SO4 is our titrant because we know its volume and its concentration. So that is the definition of our titrant. Our analyte has known volume, unknown concentration. So we know the volume of NaOH, but we don't know the concentration of NaOH. So if I want to find my moles of titrant, I have to take my volume and use my molarity in order to convert it. So we know that we have 0.500 molar H2SO4. Another way of writing molar is 0.500 moles per liter. So if I want to use that to find my moles of H2SO4 using my volume, well, my volume is currently 27.5 milliliters. So I need to convert that to liters. So the first step that we're going to do is take 27.5 milliliters, divide it by 1,000, because there are 1,000 milliliters in 1 liter, and we get 0.0275 liters of H2SO4. We can then take that liters of H2SO4 and multiply it by the molarity, 0.500, and that's going to be moles per liter, where we can see that liters is going to end up canceling, and we're going to be left with moles of H2SO4. So let's pull out our calculator so that we can solve for moles of H2SO4. We'll take 0.0275 and we'll multiply it by 0.5. And we get 0.01375 moles of H2SO4. So that's our moles of our titrant. So we started our volume and we got to moles of titrant. Now we want to convert from moles of titrant to moles of analyte. So we're going to take that moles of titrant, 0.01375 moles of H2SO4. And if we want to convert it to our analyte, which is NaOH, okay, we have to look at our balanced chemical equation. So if we want to cancel out moles of H2SO4, we're going to put those on the bottom. And we want to be left with moles of NaOH on the top. Now we just look to our balanced chemical equation. We see that the coefficient out in front of H2SO4 is 1. So that gives us a 1 down here. And we see that the coefficient out in front of NaOH is 2. So that gives us a 2 there. So we properly use our mole to mole ratio. So we'll take that 0.01357, we'll multiply it by 2, and we get 0.0275 moles of NaOH. So that is our moles of our analyte. Now the goal of the problem is not to find the moles of the analyte, but to find the concentration. We know that concentration is going to be moles over liters. Well, we have moles, and something else that we already have of NaOH is the volume that we used. Okay, so in that 50 milliliters, we used up those 0.0275 moles. We now just have to use our knowledge of concentration to put those two values together and find our concentration. So before we do that, we need to take that 50 milliliters and we need to convert it to liters. So we can get 0.050. And then to find our concentration, we're going to take 0.0275 moles, divide it by our volume, 0.0500 liters. Take those, oops, forgot a 0. And we get a concentration of 0.55, let's see, how many sig figs? 3 sig figs molar NaOH. And that is our concentration of our NaOH solution. So again, we first found our volume of our titrant and converted it to moles of titrant using our concentration. So that's what we did in this first step here. We then used our mole to mole ratio that we've got from our balanced chemical equation to find the moles of analyte. And once we know the moles of analyte, since we already know its volume of analyte as well, we put moles over liters, moles over volume, and we found the concentration, which is what the problem asked us to do. Our next problem is one that you will see in your homework, and it may look tricky at first, but as long as you set it up the same way we have it set up here, it's going to work out for you. It does take a few steps, but they're not anything that we haven't done before. There's just one caveat, I'll say, on how we're going to use our ice tables for this problem. So we know that we're going to have to use an ice table because the problem states a solution is made by mixing exactly 500 milliliters of 0.167 molar NaOH with exactly 500 milliliters of 0.100 molar acetic acid. Calculate the equilibrium concentrations of H+, CH3COOH, CH3COO-, OH-, and Na+. So we know that we're going to have to use an equilibrium table, an ice table, because we're looking for equilibrium concentrations, and because we know that we're using acetic acid, which is a weak acid. So we're asked to calculate the concentrations of all species present after mixing a solution of acetic acid with a solution of sodium hydroxide. The first thing that we want to do is calculate the molar quantities of acetic acid and sodium hydroxide by multiplying the volume in liters by the molarity of the solution. This is going to tell us how many moles of each of these compounds we start off with. We want to do the moles because what's going to happen is once we mix these two solutions together, their volumes are going to double, right? We're taking 500 milliliters and mixing it with 500 milliliters. That's then going to create an overall solution of 1,000 milliliters or 1 liter, and that's going to change those concentrations. So if we know the mole values instead of the molarity values, it becomes easier to solve for. Okay, and since they're all being mixed together into the same container, the mole values are just an easier way to represent them specifically in our ice table. So the first thing that we want to do is find the mole values, mole quantities. Let's see, our moles, I'm going to represent moles as N. We always show moles as N when we worked with, entropy, enthalpy, when we were looking at moles there. We were looking at moles in gases. We always use N, so moles is N. So moles of acetic acid, I'm just going to show as AA. Okay, we're going to take our volume, which is 500 milliliters or 0.500 liters, half a liter. And we're going to multiply that by its concentration, which was 0.1. Okay. So that's going to give us 0.5 times 0.1. That's going to give us 0.05 moles of acetic acid. Then we can do the same for NaOH. Okay, so we had 0.5 liters and our concentration was, what was it, 0.167. So we'll take 0.5 and we'll multiply it by 0.167 and we get 0.0835 moles. Now what we know about NaOH, since it's a strong base, the moles of NaOH are going to be equal to the moles of Na plus as well as the moles of OH minus. Okay, that's the same thing that we talked about when we first introduced strong acids and strong bases, that they fully dissociate so that their mole values and their concentrations are all equal to each other. So that's going to help us in the future when we're solving for our concentrations here. So now that we have our molar quantities, this is when we want to set up our ice table. Okay, so we have our initial amounts of each of these in solution, which means that we can then solve for our equilibrium values. We know that ice tables can give us a lot of that information. So I'm going to start with my balanced chemical equation. So I'm going to show acetic acid plus OH minus is in equilibrium with acetic acid minus, to show that it lost a hydrogen, plus some H2O. And we're just going to ignore H2O in our ice table because it's a liquid and it is not going to contribute. So let's look at our ice table here. Okay. So I know we've always put molarity or concentration values into our ice tables, but again, since these are all in the same container, it's just easier to use the molar quantities. So the mole quantities that we calculated before, since once we have our equilibrium mole values, we can then calculate the concentrations using the 1,000 milliliters. We could technically do that first and find our concentrations this way. It's just easier to put in the moles rather than to convert them back to concentrations, I promise you. So let's just do it this way. I know it's a little funky, but it's the same concept. So our initial concentration of acetic acid was 0.05. Our initial concentration of OH minus, or molar value of OH minus, that's this guy here. We know that it relates back to the NaOH, so it's going to be 0.0835. And our initial concentration of our acetate ion is 0. Now, with this ice table, we know what our X value is automatically, because we know that this is a neutralization reaction and essentially all of the acid is being used and neutralized with the base. So all of this, all 0.05 moles of that acetic acid are going to be used up in the titration. That's the definition of a titration. The equivalence point is when I've used up all of my acid and enough of my base to neutralize my solution and create my product. So my X value, instead of writing minus X or anything, we're just going to say that this value decreased by 0.05. And that our acetate ion value increased by that factor. So I had to create that ion. Okay, so that is the one difference in these ice tables as we're solving them in these homework problems. Okay, so whatever your acid mole value is, that is going to be your X value, because the definition of a titration is using up all of that analyte, all of that acid, and with enough base to complete the reaction. So that tells us exactly what the X is. So that gives us an E of 0. We could do 0.0835 minus 0.05. Oops, I did multiplication. 0.0835 minus 0.05. So that's not how math works. We get 0.0335 and 0.05. So these are now the mole quantities at equilibrium. The only slight change is going to be the acetic acid. There will always be some acetic acid in the solution. It doesn't fully get used up because it's in an equilibrium. So even though we have a lot of that acetate ion, there's still going to be some acetic acid left over. So when we get to it, I'll show you exactly how to solve for that value using our other concentrations, which we'll calculate here. So that brings us to our third step of solving this problem. And that is going to be calculating the concentrations. And we have to remember that our final volume here is going to be 1 liter. So when I mix 500 milliliters with 500 milliliters, I create 1 liter, and that is going to be the new volume that you used to find the concentration. So the easiest one to find first is going to be the Na+, because the Na+ is not participating in that reaction. So the number of moles that we have of Na+ is unchanging in this problem. The only thing that's going to change is the fact that the solution was more dilute by mixing it together. So what we are going to do is the concentration of Na+. It's just going to be the moles of Na+ divided by the final volume. So we know our moles of Na+ is going to be our moles of NaOH. They did not change in the reaction. They're an ion that's just floating around. So we take that, let's see, 0.0835 moles, and we divide it by 1,000. 1 liter. I'm in too many different units. Divided by 1 liter. So that gives us a concentration of 0.0835 molar for our Na+. Now we can do our OH-. We know from our ice table that the equilibrium mole value of OH- is 0.0335. So we just have to take that and divide it by 1 liter to get our final concentration of 0.0335 molar for the OH-. And we can do the same thing for our acetate ion, so our AA-. It's just going to be that mole value, 0.05. We'll add 2 more decimal places on there for sig figs, divided by 1 liter to give us 0.05 molar. So those are the first 3. Those are the easy ones. The difficult ones are going to be the H+ and the acetic acid concentration. However, we can use the information that we already have to solve for those values. Specifically, we can use H+. For H+, we know that, let's see, I'm going to write this in a different color. And we'll write it not as an equal sign because it's not the math part. We know that Kw is equal to the concentration of OH- times the concentration of H+, right? We learned that when we started talking about acids and bases, and we showed how that can be derived. Well, we know OH-, it's right there. We know Kw, that's a constant, so we just have to take that 1.0 times 10 to the minus 14, plug in our OH- concentration, and we'll get out our H+ concentration. So we just take 1.0 times 10 to the minus 14, divide it by 0.0335, and we get an H+ concentration of 2.98 times 10 to the minus 13 molar. I'll highlight that. Okay, the last one is going to be the acetic acid concentration. Okay, and I said that this one, although it's going to be essentially 0, it's still going to have a value because it's an equilibrium. So there's always going to be some of that reactant left. It's just going to be a very small amount. So what we can do here is something similar to what we did with our H+. We know that Ka is equal to H+, acetate ion, divided by acetic acid. And we know Ka, we now know H+, and we also know the acetate ion concentration. So all we have to do is plug in those values that we already know and solve for our acetic acid concentration. So we know that Ka is going to be, is it 1.75? Yeah, 1.75 times 10 to the minus 5. And that's going to be equal to our H+ concentration, which is 2.98 times 10 to the minus 13, multiplied by our OH- concentration, which is 0.0335, divided by our acetic acid. Okay, and now we can just solve. I'm going to do the top, 2.98 times 10 to the minus 13, multiplied by 0.0335, and then I'm going to divide that by 1.75 times 10 to the minus 5. And we get an acetic acid concentration of 5.70 times 10 to the minus 10 molar. So again, it's a really, really small concentration because we basically used it all up, but because this is a weak acid, it'll never fully dissociate in water. Okay, so it'll never fully react. We are always going to have some of that acid left over. So again, you will see this type of problem on your ALEKS homework and in your chapter exam. So again, if you follow the 3 steps that we have going on here, you're going to do perfectly fine, and just keep practicing that so you remember how to do that when you get to your exam.